Okay, so to start getting a feel for what these Lorentz boosts are going to do, let's just do one and see what happens. So if you remember, I defined our Lorentz boost matrix as the following. So this which I've written here, this 2 by 2 matrix now, is going to be the Lorentz boost matrix between the x and t coordinates. So for simplicity here, I'm going to work again just on a 2-dimensional or a 1 plus 1 dimensional space-time, ct and x, because a Lorentz boost is only ever going to affect one space and time coordinate at once. The rest of the matrix, if this was now a 4 by 4 matrix, it's just going to be 0 there, and then my density on that bottom block. And so all the effects of boosts can be seen just simply working in 2 dimensions. So for simplicity, that's what I'm going to stick with. So now this boost matrix we see depends on this parameter psi, which I'm going to realise shortly, but for now I'm just going to tell you it's going to be some real parameter that we're going to realise is actually also going to be an affine parameter, i.e. it runs through the entire real line from minus infinity to plus infinity. But for now it's just a real parameter. And so what's actually going to happen now when we perform this transformation? Well, we're going to arrive at some new set of coordinates. Let's call them c, t hat, and x hat. These are going to be our boosted coordinates. And now let's see what these new coordinates are going to look like. So let me just write out now in full this matrix multiplication. We can see what's happening. Okay, so simply multiplying this matrix and vector together, we get the following vector, which now gives our new coordinates in terms of the old coordinates. So this isn't really too helpful to look at by itself, but let me just rewrite it and then I can start drawing some pictures. So I'm just going to rewrite this up here. We've got that our boosted coordinates, the hatted coordinates, are then given by this combination of our old coordinates. Okay, so what I really want to stress now is that these don't be thrown off by the appearance of these cosh and sinh. Although it looks more complicated than it is, essentially cosh and sinh is just some number. It's just whatever value cosh psi has at that point. And this psi is the only thing which is going to change. What we have to now realise is that the boost is going to be now a continuous matrix which is parameterised by this psi. And we're going to see what this psi corresponds to shortly. But for now, let's just consider what we've got here. What we now need to realise is that this is, first of all, it's going to be a linear transformation of our coordinate axes. So we're starting with our regular x coordinates, and then we're applying the Lorentz boost to those coordinates. And now we just have to look at these new t hat and x hat coordinates. We can write them in terms of the old coordinates, and we can just now plot on this figure what these new coordinates are going to look like. And so there are a number of ways you can do this. Probably just the easiest way is to go to some graphing application that is going to let you input some kind of parameterized thing, i.e. you want some kind of ability to have some slider that you can change this value of psi, and you can use that to see how this transformation is going to affect your axes. So I'll put in a little clip of me doing this shortly. So once we've seen this clip, we can now understand. Basically, these new axes, they're going to scissor together in the following way. Okay, so I'll just draw what the transformed axes are now going to look like, and then we can start interpreting this. So this red line which I've drawn is going to be the x hat axis. And now this blue line which I'm about to draw is going to be the t hat axis. If I can draw a straight line. So maybe it will now be helpful if I colour code these over here. So the red line is x hat, and the blue line is our t hat coordinate. So let me just be absolutely clear what this figure is now. Because our manifold is just essentially R2 or R11, this is our space-time. I've drawn in white one reference frame on that manifold as a kind of orthogonal set of axes. But now I've juxtaposed on that same figure, I've drawn now another observer's reference frame of this manifold. So both of these axes are drawn on top of the same manifold, and now what we're seeing is how these two observers are essentially assigning different number values to points in this space-time. If we take any point P in our space-time, if we look at its unboosted coordinates, it might be, say, xp, tp, but then the coordinates in these, now the boosted frame, are going to be a completely different set of numbers, and in fact they're going to be measured in a slightly different way. So what happens when we draw non-orthogonal axes like this is we have to now realise that we're not working with a Cartesian grid anymore. So the Cartesian grid is coordinates that look like this, and you measure points by giving their Cartesian components like that. But now when we boost these axes, we see that they're kind of skewing together. These square grid lines are also going to be skewed. So effectively what our new coordinates are going to look like, they're not going to have square axes, they're now going to have these kind of parallelogram looking coordinate cells, if you like. And so the coordinate values at any point, we have to realise, well, we're going to measure them in a similar way. So if we were in Cartesian coordinates, but let's now say that if this white blob is the origin, and I want to give the coordinates of this point, I have to realise that its coordinates are not given by an orthogonal projection to the origin, but now rather a projection that goes along these coordinate diamonds, if you like. And so maybe a better way to understand why this is the case, what we now have to realise is that this line x hat which I've drawn, we usually would understand this as being the x hat axis, but now a better way to interpret this line x hat is that it's really a line along which this t hat coordinate has a constant value. So if you stay somewhere on the line x hat, effectively if you just remain on the x-axis, the t hat coordinate isn't going to change. And just comparing this really simply with our orthogonal picture, that makes a lot of sense. If we stay on the x-axis, the x-axis is effectively always at the same t equals 0 position, and we need to realise the same thing happens even if these axes are now skewed. Everywhere on this red line is the line on which t hat is equal to 0. And so in our new coordinates, we have to realise that lines of constant x are the lines parallel to the x-axis. No, sorry, lines of constant t coordinate are now lines which are parallel to the x-axis, and lines of constant x are now going to be parallel to the t hat axis. And so the coordinates of any point we need to measure by basically tracing back to what constant value that corresponds to. So the key thing we need to now realise is that in these shifted coordinates, we can no longer think about orthogonal axes. We instead have to think in terms of points on which one coordinate value has a constant value. And so we should rethink the x-axis as rather being the point on which t is some constant, and likewise with the t-axis, this should instead be thought of as x is equal to some constant. And so when our coordinates are skewed like this, we have to remember that these skewed lines are corresponding to constant values of one of our coordinates. So this straight red line would be the value on which t hat is equal to some constant. And so don't worry if that's a bit confusing, we're going to explore this much more and it's going to become more intuitive once we start looking at some values. But for now this is just, at least geometrically, what this boost is going to do. It's effectively just taking our orthogonal axes and kind of skewing them together. But now let's try and come up with, physically at least, what this is actually corresponding to. So I'll just rub out a bit of this to make some more space.